already?
Yeah, today I want to start with domain walls and symmetries. First place in rational component field theory, but then after some time I will say something about other theories also. So to start with, we call the domain walls, well, in 2 dimensions, these correspond to lines, for topological defect lines. In rational conformal field theories are objects in the category A prime bimodules. So this means that we have such a defect on the worldsheet. Then on one side of it we have A, and on the other side A prime. And the line is oriented, and we use this notation actually in literature sometimes for the bimodule when you, this is now an A prime bimodule, clearly A is from the left, but sometimes the direction of the defect lines is taken opposite to that for some good reasons, but one has to then to be careful. Now, in the case that A is A prime equal to A prime, then this is clearly monoidal, where just the tensor product over A, defined as a co-equalizer, as we have seen, is the analog of the usual tensor product bimodules over a ring. Now, we are in the situation with 2 different defect lines, of different type. Say an A prime, and A prime, A double prime by module. Then we still can use the same prescription as for the tensor product here to get a kind of algebroid structure. And in the particular case in which we are here, in rational conformal field theories, we deal with model tensor categories. But for what I'm doing now, I essentially only need that the category is abelian, therefore in particular idempotent complete. I can actually describe this as this would be over A prime now, as an image of an idempotent. So in this situation, I don't write the orientations for simplicity. We have a left action of A prime on this B and this B prime, and the right action and the left action on B prime. Then our algebra will. I forgot this. A is now special Frobenius algebra, in fact also symmetric, but here we do not use that. Then we can take the tensor product of B and B prime over A prime, which is then an A double prime bimodule, as the image of this morphism. And this morphism is an idempotent, which is easy to see. Let me just indicate it. If we have this morphism twice, then by the representation property applied here, we get lines like that, and on the other side analogously, and then we end up with this picture. But by using the Frobenius, so this is a representation property, by using Frobenius. This is the same as this picture. And then by using special, this is the same as and this multiple only once. Any kind of interval, but which explains a bit more about this situation. If we take into account that in the application in rational conformal field theory, these algebras were important as algebras directly for the construction, but the results are depend on A essentially only up to Morita equivalence. So we should remember that from A we get a module category M over C. So A is an algebra in C. Such that M is equivalent to A mod, where if I take less A modules, then I get right module categories, and the formula is simply that acting with an object in C on the module M is, well, I have to describe this as an object together with the object, the underlying object here. So then dot row as an object in A mod, and then I have this action by taking the tensor product and then just row times the identity C, and then you can check this naturally again an A module. Also, you can go the other way around, but I will not talk about that because we will take this in more detail anyhow another time. Now, in this context, remember also that we, when we have a module category of several of them, for several algebras, then we have module functors between them, and in particular you can consider the category of module functors, C module functors, say from M to M prime, and this now actually turns out to be equivalent to the category that we have here. Depending on, and I haven't checked whether I have to consistently use the same convention. It could also be with opposite tensor products, depending on whether you talk about right and left in this way or left and right. This you simply get by taking in this direction, you map a Y module to the functor which is given by tensoring over the so this I take an A module, now it's for right modules, I'm sorry, right module, and a tensor by module from a right A module, I get right A prime. So you can check this, it gives you a functor and actually an equivalence, and in particular, you can look at a special case that M is equal to M prime. Then you deal with the category ender functors with respect to being C modules, and this is often denoted by C, M, and star, and sometimes called the dual category. I'm not sure how who this terminology is, but in any case, the notation is generally used. And then if you look at this together with composition of functors, then this is actually monoidal. And you can check also rigid. You find this in the, for example, in the Ettinghoff et al. Book 1. And also, I don't write this down after that. You show that if M now right C module category, then it's also a left CM star module category, and in fact a bimodule category over those. Also, if you impose certain natural properties, which we have in the case of conformal field theory, then you get nice properties for this functor category. For example, if C is a finite tensor category, generalizing rational conformal field theory, and M is indecomposable, then also the dual category is a finite tensor category. And next, I want to talk about the fusion rules of these categories. Let me see. Yes, in that context, I will say a little bit more about the functor categories. So we now take C, a modular fusion category as a rational conformal field theory, and M to be a semi-simple indecomposable module category over C, and also non-degenerate. And I do not really want to explain what that means in detail. And then this situation, for example, in the case that we have semi-simple category, no, actually, I'm not sure whether this is an extra requirement. I didn't check that. But in this case, we have that the complexified Grothendieck ring. I called this GR before, but in order not to mix up things, I follow my notes. I write K0 for it. So if I look at the category of a bimodule, or A, well, A corresponding A such that its modules are equivalent to M, then one can write this algebra, which we often call fusion algebra. Well, as an algebra, you can show it's isomorphic to direct sum over lambda and mu in lambda, the set of isomorphism classes of simple objects, over the endomorphisms of the following, the linear endomorphisms of the following, maybe I should write that first here, on AA, and then expression that we have seen before, namely when we describe bulk fields. But this was the space of bulk fields with chiral labels lambda and mu in a phase of the full conformity theory described by A. And now, this is a result which was originally conjectured by Ostrich and then later on later shown by using conformal field theory methods. And in terms of this dual category, this can also be described. These morphisms here can be described as morphisms in CM star. You know, these are equivalent. And then we have here certain, well, these are now functor categories, so I need certain functors here, and I call them alpha plus and alpha minus. Okay, from y lambda or y mu, respectively. And these functors in the literature are sometimes called alpha induction. Because when we use the letter alpha, I prefer the term braiding induction. And they are described as follows. So there are functors from M to itself, where I send a module to alpha plus of, let me write just U, where U is an element, an object in C. I send this to the object in M, which is given by the action of U, and these are not just functors, but module functors, and the module functor structure is given by the following.
What is the definition of KT?
Oh, Grundig ring. What's another notation? Actually, the non-semi-simple case, in some part of the literature, there are two different. These are two different things, but I'm assuming semi-simple anyhow. So maybe I should have followed my previous notation. But when writing these notes, I didn't. So what is the module functor structure? On these, well, we have that we take two objects, U prime and U in C, then this is via the braiding in C, with isomorphic to object where I use the opposite order in tensor product, but this here is isomorphic by definition. And I have to look at this to M run by M and then applying U, which is alpha. Sorry, this is by the representation, by the module category structure, and by definition now this is the same as alpha plus minus of U applied to this object, whereas here is isomorphic. If you apply exchange, which then is by definition the same as alpha of U applied to N, and then my U prime. And so this gives us a module functor structure, and also let me mention, if I take U V E in CM star, U prime, map it to alpha plus minus of U, which is a functor composed with B, which is a functor composed with alpha plus minus prime of B prime. So here some choice of plus minus, and here some possibly different choice. Then via these 4 different maps that I get one CM star becomes actually CM CC by module. So I have
prime here. So on the right hand side, it should be alpha plus minus U prime, and then X
no,
by
it's
U.
not
No, on top.
on top.
Yeah. U prime.
No. This you apply to
Okay.
is
You write it inside. Okay.
acting on endless. So up to this point, I haven't talked about CFT, but now I will do that. And for this, I mainly use pictures and not try to avoid formulas. So we are in the situation that C is a modular fusion category. M is a module category, say isomorphic to A right modules, and A is now a simple special symmetric covariance algebra in C, and I will now give make some statements without trying to prove them, but all of them can actually be proven in with the help of the TFT construction of coordinates that I presented last time. A is first, we have fusion of defects. So what I said about bimodules is now true for defects. So these now you should think of really as ribbon graphs in the sense of last time. And for some reason, I now started to call the defects the labels X. So this is I can replace locally on the worksheet by where here I have the bimodule X tensor over A prime. Then I can use the boundary. So if I have a defect, and here a segment of the boundary, let me indicate this in this way. And remember these the boundary conditions are labeled by objects in the module category M. Then I would have this situation. So this would maybe I should write N prime, but now it's an N prime module. An A prime module, then this amount is looking at the situation where I actually have A module given by labeled by the tensor product over A prime of X with N, and now I did it again wrong. So I'm now talking about left modules. I'm often confused about that because in the conformal field theory literature, one usually uses left modules over algebras, whereas in the mathematics literature, one usually uses left module categories. But if I have left for one of them, then I have right for the other. Could be that some of the formulas that I write have that I will make the same mistake. Then I have defect fields or defect changing fields, if you wish, which correspond to the situation that we have a defect x prime here of the same type. So if I have a prime here, will be the same on this side. And then the labels for these morphisms are correspond to these morphisms are elements of the bimodule morphisms between x and prime. Then I can look at defect junctions. So I have more generally the relation that I have, say, two or several, but defects coming in, one coming out. Then I have a double prime say here and a prime here, and then alpha will be in the morphism space of a and double B. Your prime modules from x vector over a prime double prime. And there is in particular what is called the invisible or trivial defect. Remember in our string diagrams for monoidal categories, since we implicitly assume strictness, the tensor unit is not visible, and in the same sense indicates that A is equal to A prime, you have situation where there is the invisible defect, which corresponds to the tensor unit of the category of A1 modules. And then also you have can have fields, special defect fields, where one of the two defects involved is the invisible defect. So this situation, and of course you can have such morphisms only. Since again, we were in a semi-simple situation when the defect x here is isomorphic to a plus something, and these fields are on disorder fields. This is the term very common in the conformal field theory literature. And let me mention that by semi-simplicity, we can in particular we know that each defect x is a direct sum of simple bimodules, or bimodules labeling defects. So this can be written as I have a prime here, a sum over, let me call this kappa, in the corresponding set, which now would have labeled subscript A and A prime, of simple bimodules and sum over morphism spaces alpha, and then I have here alpha bar, which refers to the vector space dual. So if I choose a basis here, then alpha is assumed to correspond to the basis. Then alpha bar will be the vector space dual basis, and then write this as a sum where here have a simple defect. It's kappa. And again, by simplicity, you have this. Analogously, you have the situation that you have two the simple defects now, x kappa and x kappa prime. Maybe I should write x prime kappa prime because this will be in a different set. If a prime and a are well, at least two of them are different, but then you can write this as a sum over kappa, sum over beta gamma, and no, sorry, sum over beta, and then an analogous situation here. Simple object x, this would be kappa double prime now. X kappa double prime. Be very precise, x prime, double prime, kappa double prime, because again, different. And then which is over here we give now an a double prime bimodule, and this is a relation which can be used conveniently to simplify ribbon graphs. Well, to make them more complicated, but once you have done that, and then use properties of these basis morphisms, when you have many of them, then things can become simpler. Or in order to get explicit formulas where you have the various structure constants. Let me mention another one where I don't draw the left-hand side again because it's the same, but or almost the same. I now use a notation which I have previously avoided because I don't like it. Implicitly, well, already with the orientations I have drawn here, in principle, I could have omitted because I always read these ribbon graphs from bottom to top. But if I interpret these as ribbon graphs, but now we want to interpret them both as ribbon graphs when we calculate with them as morphisms, but also concretely they will appear in the TFT construction as ribbon graphs. And then the ribbons are oriented, and we can also look at this situation. But this would correspond. We are in particular a pivotal situation. So unambiguously, this corresponds to an x2 line in the other direction. But since I was using some graphs from the literature, I use the convention there. So in this situation, you can need a bit more space. You can also prove the following. well, you reduce it to this one, essentially. Now you have some, no. A different type of morphism here, but again, here the vector space tools, and namely those which are of this type. Respectively of this type. No, that. So here I would have left and right dualities, but again, in a pivotal situation, unambiguous. And this now holds up to some vectors which are given by dimensions. And to show this, essentially, you close the line here and then use some rearrangement, and then insert the previous one. Then they differ by a closed loop, which is a dimension. So all of this is still not related to the second keyword I had the first line today, the symmetries, but now we gradually get to that. So what we can now do and then calculate using the previous results with it is to wrap a defect around the bound field. And let me first draw this schematically. So we have a boundary which are indicated in yellow here. So it's not one of those phi's. And then we can look at the situation that we have. Some defect line here and some other defect line which goes around like that. Copper, let's say, this is an AA defect, and here we have a prime defect. And now this can be replaced by the situation where we have only the copper line here, and now here we have one of these special defect fields. So this will be in the notation we had previously some theta field, and it will depend on the various labels that we have here. So on the label of this morphism and on the kappas, and of course on phi. Now this is schematic. If you remember the DFT construction, and then this was really it's a ribbon graph. This is embedded in this three-manifold MS, and the phi really corresponds to a ribbon which has two chiral labels, lambda mu, and then this line continues to one end of this double cover of the surface, and the mu here to this would be lambda, and this mu to the other part of the boundary, and then in addition we have our A, this was A prime, dual triangulation here. So there would be a representation maps here and here. And well, depending on how I orient them, if this really is like that, then I would have to insert unit and co-product here, but that's just a technical detail. And then analogously on the outside here, I will have part of the dual triangulation of the A parts. And this means that you have, when you want to tell what this precisely is and what its properties, then you have to be careful about the gradings. And as a special case of that, let's assume that X kappa is just an invisible defect A, so this line goes away. Then you get the situation that of the following type. I draw it again just schematically. So you have this X prime line here, surrounding bulk field, and then you get well, here you have such a disorder field, but now this line is away. So what the new field that you get is a new bulk field phi prime. So by wrapping a circular defect around the bulk field, and this works once you do it correctly with the ribbon graphs, you get another bulk field. And that means if you do this inside a correlator, you relate correlators for certain bulk fields or equate them to correlators for other bulk fields. That's what we call the symmetry of the field. A non-chiral symmetry, one could call it. And nowadays, often people call this a categorical symmetry. But the important thing is that it's of different type than the chiral symmetries that we have in the underlying vertex operator algebra. And let me continue for 4 minutes. Now we can use this together with the following. Assume we have one part of our worksheet which is in phase A. We look at the same thing again, but then we insert in this a defect, a circular defect, which is surrounding nothing. Well, no field inside. So we would have A here and A prime here, then X is an A prime defect. And then this situation, you get the same results for correlations here, except if you look at it in a bit detail up to dimension of A divided by dimension of X. So at the cost of such an extra very simple factor, you can just insert such a circular defect somewhere on the worksheet. And now, let me see, there is some, this was not a 1. This is a 9. So we can, for example, look at the following situation where we do have bulk fields, with 4 of them, because that's a particularly interesting situation. If the worksheet is a sphere, but I don't indicate this here, we can start with this situation, and up to this vector, which I don't write, we add such a defect, circular defect line. But remember, these are topological, so we can deform them as long as we do not touch any fields. So we can come from this to the situation that things look like this. Let me see to do it right. I think it's right. That. This would be a possibility. If this is on the sphere, now I'm using sphere because then I'm going on along the backside of the sphere. And now in this part of the picture, we have something which looks close to what we have here, but not exactly. And after the break, we will look at a situation where actually these two situations are the same. So now we introduce a special type of defects, namely those which are in a suitable sense invertible. We say that X, which is an A prime defect, is invertible if and only if there exists X prime, which is then an A prime A defect, such that if I take the tensor product over A prime, I get back A. And we'll leave this picture for now. Continue here. The lemma for X prime as a definition. The following holds. Plus X and X prime are simple defects. Then X is isomorphic to X prime dual as A prime bimodule. And analogously, X prime is isomorphic to X dual as A prime A bimodule. And the analog of this here with opposite roles, the tensor product over A prime of X prime with X is isomorphic to A prime. You see, this doesn't make sense. A prime. Tensor. Now I have to check whether I did it correctly. So X is an A prime. Yeah, so this is an A bimodule. There's a prime missing here. And now X prime is an A prime A bimodule, but this is the statement. And I don't write the proof for this, but just mention that one thing one uses, and otherwise the argument is preferably done with urban graphs that we got A double prime bimodule morphisms for X tensor A prime X prime within X double prime is isomorphic to the other atoms. A prime and double prime bimodules X prime X dual tensor over A. And also, maybe I mentioned this, that if I do multiple tensor products, then up to isomorphism, the order does not matter. So this is isomorphic to X tensor A prime tensor over A X. But this by assumption is isomorphic A and A tensor over A. Another lemma. Is that we can remember this picture, I think. If this is where we easy generalization of what we have for invertible objects in a monoidal category. If X, the same type as before, is invertible, and X prime of the same type is invertible, and then the tensor product for A prime is invertible. So that means that if I look now at isomorphism classes of invertible A bimodules, A prime, then I get a group structure, and this is just the Picard group of this bimodular category. And this suggests that actually invertible defects are well, various aspects of them can be understood with the help of structures in the Picard group. And one thing one should mention here is that in the situation with modular tensor categories that we had before, they were braided in particular. The Picard group is abelian, but there is no braiding of bimodules in general. So this can be non-abelian, and there are already in very simple examples it actually is. And another consideration is the following. And now using this description of the tensor product in terms of the image of this idempotent. So this is the same as the corresponding tensor product. I don't want labels at all. And if I now take traces of this, then using also the fact that if I look at this piece here, say, this is a morphism from A to 1. We assume that our algebras are simple, meaning simple as bimodules over themselves. And it follows from this that this is a multiple of the unit. And then you see that you can simplify this, and the result is that the dimension of x squared, so if you assume this is x and this is x dual, divided by the dimension of A, what we get from the left side, and here we have clearly, sorry, this. I should have before. We look at a situation that x tensor over A is so invertible AA bimodules, and then the right side just dimension A. And from this, we see that the dimension of x, divided by dimension of A, which, as I mentioned in the break, is the same as the A dimension of x. So the dimension of x as a bimodule, as a bimodule, sorry, is the same as takes values in plus or minus 1. So the dimension of an invertible defect in the A dimension can only be plus or minus 1. One can say a bit more. In some cases, the minus 1 is not appearing. Namely, no. A and A prime be symmetric, simple special symmetric covariant algebras, and X a simple and invertible A prime bimodule. And assume one of two possibilities. Either there exists a Y, which is then necessarily an A prime A bimodule, such that X tensor over A with Y. No, sorry. Let me see. No, this should be an A bimodule and Y a prime bimodule, such that the tensor product over A here is isomorphic again to Y, or there exists a Y prime, which is then an A prime A module, such that Y tensor over A prime, no, over A with X equal to Y prime. One of these holds, then actually the A dimension of X plus 1. And the argument is precisely the same, of the same type as here. Now you have X and Y on this side, and then one of the dimensions cancels out on both sides, assuming dimensions are non-zero. I'm suppressing this. We assume that for example, that the dimensions of bimodules cannot be zero. This is guaranteed, for example, if dimensions as objects cannot be negative, which in turn is guaranteed in particular if the category is unitary. But I don't want to talk about that. So I always assume actually. And then almost in the point to which I mainly want to come here. So we call this identity we had. That the tensor product that has two parallel defects can be written as a sum with certain prefactors over simple defects like this. Now assume that one that let me call this kappa prime, double prime was this was x kappa up to dual maybe. Assume now x kappa is invertible. Then if you look at this equality, you see that it follows that up to a number this is the same as this picture. Again, I'm implicitly using pivotal structure. And then again, by taking traces, you see that the factor epsilon that you have here is nothing but a dimension, the A dimension. You really deal with tensor. No, not. I have to check that. Now, if you now look at this equality and insert it at these places here, then you get a situation where on the sphere, but similarly on other surfaces, you have these original bulk fields, and then you simply have circular X lines around them. And as I said before,
So this epsilon x is also -1, I'm saying.
I thought so. Then this would be the dimension, A dimension.
Yeah.
But from if I look at the picture now, which is drawn as a graph in C, then it seems that it's actually the actual dimension, the upper dimension.
Yeah. So this pictorial, this graphical notation here is a bit confusing. We are doing it in bimodules or.
Oh, you're right. So this is actually in the situation that this should be considered as obtained from part of a ribbon graph, and then again there are A lines attached here, and therefore you get it like that.
Yeah.
And I should make a note here. And more generally, if I'm at a situation that I have any bulk field locally, and I have some defect, invertible defect here, then I can deform it like that and apply my equality here and deform it again, and what I get is the situation where the X defect is on the other side, and here I have this different bulk field is multiplied by ±1. And then in particular, that means in this situation, I should have, remember here there was a factor of dimension, which is now again epsilon, and then here I have 4 factors of epsilon, but each of them is ±1, so here there's no additional factor. And similarly, so what I get in any case is by pushing through a defect through a bulk field, I get another bulk field, and therefore, if I do this in correlators, I get a relation between correlators of different bulk fields, and that means it's symmetry. I will give you one example, but let me first just mention that how you can interpret the sign. If I include the chiral lines here, then you see what this involves is actually a double braiding of phi with one of those lines, and this gives rise to such effect. Then similarly, you get actions on boundary fields, actions on well, we have in general seen actions on boundary conditions. Now we have a special case on that, and so on. But I will not say more about that. Instead, just give you an example. Is one conformal field theory that as a non-conformal field theorist you should know about. This is the critical easing model. It has conformal central charge 1/2, and it has up to isomorphism 3 primary. There's three simple objects which are the monoidal unit, and then two others which are often denoted by sigma and epsilon, or sometimes psi. Circumstances, and their dimensions are 1 squared with 2 and 1. This is an invertible object. And now, if you just take your algebra A to be the tensor unit, and there's a bijection between objects and bimodules, so we can look at, in particular, the epsilon effect wrapped around fields, and what you get is, if you around 1, then you get 1. If you wrap it around psi, you get psi. And if you wrap it not psi, they call it epsilon. And if you wrap it around sigma, then you get minus sigma. And well, maybe I should have called it psi, because I called the sign here. It's a common notation. But it's so much about symmetries. But it's not the end of the story. There's a generalized notion of symmetry, which sometimes are called duality symmetries, or, as I said, categorical symmetries. And this is related to what I call duality defects. The example was before. Now, remember that in the general case, we have the situation like that we have a bulk field, and then we can look at the effect around it. I omit now all labels to save some time. I can write this as a sum of terms where I now have a disorder field here, where this is over kappa and these are simple defects. Some morphism and some over beta also, where this is beta, and x. And where, say, this is the A prime A defect. And now assume I have another defect, which is an A prime defect, where I do the same thing. You see whether maybe I take a slightly different color. X prime. And there's another thumb here. And I have, no, wait, let me first draw it once. And this becomes a sum over more terms where I now have something complicated, but now let's assume that this way I end up again with a new bulk field. Sum over bulk fields. So that means there will be morphisms of this type. Here's my x kappa. And then I have x prime, x prime. And if this holds, then I call X duality bimodule. So it works if there exists an X prime such that pushing through both X and X prime it gives me, apart from more endomorphisms of X tensor X prime, only bulk fields up to prefactors, then I call it a bimodule. And wait. For some reason, I switched here to 79 because probably again I could not read my own handwriting. There's the following lemma. X is a duality bimodule if and only if the tensor product over A prime of X dual with X is isomorphic to a direct sum of simple invertible, well, invertible implies simple, we have seen bimodules, possibly with some multiplicity. Where the label here is well, it's some it's invertible, and we know this form the part of a bimod, and in order to indicate that it's a group, I now use this let's G instead of kappa. And how do you prove that? Well, you look at this picture, you insert the one of those relations that we had, and then well, in one direction, where we have the sum over such intermediate simple modules, if all of them are invertible, then I can use this identity to simplify the picture, and then what I get is something which precisely looks like here. This direction is easy. In the other direction, I have to assume that this is the case. and then use the fact that these parallel lines I can replace by a sum over terms where there are only simple objects, and then I take the trace of both sides and move around. When I do this twice, move around and use duality of the vector space basis, and then you end up with the result. It's a bit lengthy, but it's not so complicated. A bit more difficult is the following. To prove is the following result, and I will not say anything about the proof, which is that not only do we have here some simple, some invertible simple modules, but in fact they form a subgroup of the Picard group, and then the multiplicities are equal to 1. So, and this holds if X is a simple duality bimodule. Unlike the case of invertible bimodules, which are always simple, duality bimodules need not be simple. This holds also if they are not simple. If they are simple, then we can strengthen this. This is isomorphic to the direct sum of xh, where h is in some subgroup H, where H is the subgroup of the Picard group. Which are precisely these. For which X is a fixed point in the sense that the tensor product over A prime of X with Xg is again X. Of course, this depends on X. Maybe I should find X here. And maybe I should call them something else than X, because I use Xg for the simple, for the invertible ones, but there are only finitely many. Let's review this now. And also, in this case, a different result. In this case, the torus partition function. Of A prime. So X is here an A prime A bimodule. Can be written as linear combination of ZA torus correlators with defect line insertions. And then we just indicate this graphically. You know, the torus in this way with identifications. A prime here, and this is the same as the sum over 1 of H, the size of Hx. But this is, I can take out the sum H prime in Hx, such that they commute. the commutator subgroup of the following picture. So all of this is in A, and I have prime modules, and one of them, let's say H or XH, goes here, and the other one say goes here, X prime, and then let me just write this like that. So here this there is a corresponding morphism in the relevant morphism space.
Like a kind of orbital construction.
Precisely. The next sentence I want to make. This is sometimes called an orbifold construction or identity. And the idea of proof is not so hard. Remember, we can insert at the price of a vector in a line, an X line here, and then we deform this on the torus, and we decompose X into simple bimodules, well, X, and then we have parallel lines of X and X dual, and use this result here. This was 70 with this numerology. Then let me add one example of that. Well, let me add also an example for the 4-point function, again for the Ising model, where I use the results that I have done before. If I have 4 of the sigma fields, well, sigma meaning both left and right I will label equal to sigma, and this on the sphere you can show by inserting a duality defect, which is there's one duality defect, one simple one, namely sigma. You can show that this gives you the same as having the disorder fields, which are typically denoted by mu, which chirally have the same labels as the sigmas because I don't change them. And then there is an epsilon defect between them. And as an example for this torus thing, if you look at lunch. If you look at the situation that we have a torus with 2 insertions of the sigma field, and one can show that this is a sum of the following 1/2 of 4 terms where everywhere I have these 2 sigma fields. Primarily the sigma fields, so they will now be these mu's. I don't write it explicitly. And in one of them, I have an epsilon defect between them here. In the other one, I have an epsilon and another circular epsilon defect around the non-contractible loop. One other where the non-contractible loop is is the second one in the homology basis, and finally another one which corresponds to going once around each direction. Then let me mention, without writing anything, that I have been careful to call this the critical easing model, even though most of the time people just say easing model. But actually, the easing model in the first place is defined as a lattice spin model, which depends on a certain coupling parameter, often called temperature, and at a certain critical number point for that number, it becomes conformal. And it turns out that these relations that you get from the duality defects actually can be extended to the non-critical situation. In that case, because they correspond to two different values of the temperature, they are also sometimes called high-low temperature dualities. And according to the first people looking at those, also Kramers-Wanier dualities in this situation. So these duality defects give you generalizations of this Kramers-Wanier duality for the Ising model. I have a few minutes left. I can come to the next part. Still, I count it as a part of this chapter 7, even though it's not about conformal field theories, but it's still closely related to them. So, and it doesn't merit a separate chapter. Effects in three-dimensional topological field theory. And I will only talk about specifically Reshetiki and Torayev defects. Topological field theories, but you can also consider similar things in other constructions. Now, let me just say very generally, if you are beyond two-dimensional conformal, and in particular rational theory, conformal field theory, then in general there's not much or even nothing that you can say, but you can at least imagine or dream that you can deal with effects which, because the blackboard is two-dimensional, I still draw as one-dimensional, but they should be considered as one codimensional, and maybe then also further higher codimension defects. So one thing is that you can hope that there is some kind of fusion process, so some monoidal structure. Analogously, you can fuse into a boundary. I don't write that down, but also then you can wrap them around fields, which would be this picture, and move through a field insertion in this way. And then typically have a sum, and there are various situations which people have looked at where actually you can argue that such structures are actually there. The only situation otherwise I know where this has been fully worked out, but I have to say I know it might be that people have worked out other situations fully also. But I just don't know that in detail. The only situation is this one, and this is where I will treat after the break. If you go to higher dimensional topological fields. So this will involve a series of fusion categories, in particular modular fusion categories. There is a notion of higher categories, bicategories, and higher, which we will treat a little bit later. And there is also a notion of monoidal bicategories then, and of fusion 2 and fusion n categories. And these have been worked out, much about them in the last few years. But I'm no expert on that, so I cannot say how much actually is known. But it seems that sufficiently much is known in order to do some of this stuff reasonably well in for higher dimensional topological field theories. Okay, maybe stop.
I'll grab my coffee.
Sorry. But did you start? Is it already recording?
Yeah.
Okay, so we can start. So remember, I said a little bit about pressure peak and Fourier topological field theory, which for us is functor, symmetric monoidal functor from the 3,2 oriented cobordism category to vector spaces over some field. And in applications, this will often be the complex numbers. Otherwise, I will assume that K is algebraically closed in any case. And in the usual description, I look at the three-manifold and maybe ribbon graphs in it, and the ribbon graphs, well, essentially are lines together with a with a framing, and so roughly one-dimensional, and you have a one-dimensional and three-dimensional piece. The three-dimensional piece is not labeled, but implicitly it's labeled by a modular modular fusion category C. And the ribbons themselves are labeled by objects, and the coupons are labeled by morphisms of C. But now I can look at a situation for codimension 1, so two-dimensional defects, let me call them surface defects, which are topological in the sense that inserting them does not destroy any of the properties of the theory, which are the origin of calling it topological. And you, of course, have to be more careful about that. But essentially, this means that you can move the surface defects around as long as they do not hit any ribbons or the boundary. And so what you will deal with is a stratified three-manifold with three strata labeled by modular fusion categories CI, C prime, and so on. And then two strata of the form. They separate a region where you have some C1 or we call it C and some C prime, and they will have to carry some label, and we have to know to decide what this label is, and the idea is now to use some arguments about moving around ribbons in this three-manifold to get some idea on this label. And this is not a mathematical proof that the label is the correct thing, but once it gives you a construction or say a proposal, and you see that this fits with what is known from examples, and it has various other nice properties. And I will do this step by step. The basic idea is that in a defect surface, we can have defect lines which are analogous to what we have done in two-dimensional conformal field theory, and in particular, two-dimensional conformal field theory contains, as a special case, two-dimensional topological field theory, where the relevant modular fusion category is the category of vector spaces. So we have inside this two two-dimensional stratum, we can have some defect lines, but also we can have defect insertions, so zero-dimensional insertion, which is a conformal field theory situation where what we call defect fields. And now we also know we have, so this would be two-dimensional. Now in our three-dimensional stratum on one side, and on the other side, we have C and ribbon graphs in it. It turns out actually that for everything that is done, one can first consider the situation that C prime is just vector spaces, so trivial, and this corresponds to actually a boundary. So what we are describing now are not labels for such topological defects, but for topological boundaries. And once we have that, the step to defects will be easy. Now what we can say is that if we have a defect here in the bulk, in the three-dimensional region, because it's topological, we can move it around, and we can do it in such a way that at some point it hits the boundary. And this way, we get from a ribbon here, or a one-dimensional defect here, a one-dimensional defect here. And also, this should be compatible with such insertions. So if I have an insertion here, it will give something which behaves in a way inherited from before. And this means that from this two-layered structure, in the category, objects and morphisms, I get something which is again a two-layered structure. So conclude that these should form a category. And to give have a name for them, called the W. There's no particular reason for the W, and there can be several types of them. So I give them another label A. Now, in the bulk, we can look at the situation that two ribbons can be brought together. That's just a tensor product in C. And correspondingly, we would we expect that we can do something also on the boundary. So this category would actually be monolic. What we can do in the three-dimensional region is also move one ribbon around the other. For that we use that the category is braided, but that we cannot do on the boundary. So this will in general be not braided, but it will still inherit something of it. Also, what we can do in the bulk is deform ribbons. We can look at the situation before and after the deformation, bringing this to the boundary. Accordingly, this should also be rigid. But this is easy. What is less clear, but what is desirable, is that it's and up to some point, right, might tell which. We do not assume that, but in order to use the results in literature, we will have this. And maybe there is no really good reason to require that, but at least we can look at a subset of situations where it works. And it turns out that has a very nice structure. So what we see from this is, first of all, we have such a category, which is very well, and we have this process, and this process should then be a functor, which I denote in this form. The next step will now be to determine further properties of this functor by again looking at various types of situations with moving around ribbons and comparing them. And the first thing, the first situation we consider is, and in order now to be able to describe this, well, to draw this reasonably nicely, I look at a situation at a section perpendicular where this is the direction perpendicular. No, here the direction perpendicular to the boundary. So the boundary is perpendicular here. So that means if I now have a ribbon here in this sense, at such a section, this will just correspond to a point. And then I look at two situations. They are written labeled by X and one by Y. Same thing here. Now I can do two things. Either I first use this functor to move both of these to the boundary. So then I get F of X respectively F of Y. And then I bring them together, meaning forming a tensor product. So I have here the tensor product of WA. Or I first bring them together in the bulk using the tensor product in C. And then bring it to the boundary, where I then get F of the tensor product. And these two situations should give me the same thing. So I require that actually there's an isomorphism here. And not only an isomorphism, but if I now have on these lines insertions, it should be compatible with them. So this is coherent, or actually forms a natural isomorphism. And that means that gives the structure of a monoidal functor. On my functor F. So this is easy. Next thing is also not hard. Remember, WA is not braided, but there is still a way or situation where we can talk about a different order of boundary Wilson lines. I now say Wilson line. I will say this often. This is a physics term for ribbon. It comes from situations in physics where some one-dimensional objects appear, and this has been well, Wilson was among the first one Wilson to study them. So it's a common practice to talk about Wilson lines. There are also special Wilson lines which then are named after other people, but those I will probably not consider. Let's look at a situation that we already have some I should have drawn them maybe in green here. But I already have some object that's called M in WA, and then another bulk Wilson line labeled by say X. Or then I can bring this to the boundary again. But again, due to topologicalness, I can deform it and bring it either on this side or on this side. So here I would have FA of X tensor or WA in WA with M, whereas here I have the tensor product in the opposite order. Well, once I have this, I bring them again close to each other. So this means, again, that I expect that there are coherent isomorphisms, and then they will be coherent between these two tensor products. The natural isomorphism of this type, and this can be expressed again as a property of this functor, and maybe here I have to introduce the corresponding terminology, definition, structure of central functor on the monoidal functor. Let's call it F from C to D, where these are of course monoidal categories, where C is graded, as in our situation here, is a natural family of isomorphism. Let's call them sigma, labels X and U, F of X, tensor in C. I call it A after that, so I will call this A. Tensor over A. You can see this tensor. No, I should do it. I call it C, and then I call it writing. So this is tensor product in D, F of X prime, to F tensor product in C. Yeah, and you have a general object in D. Such that three identities hold, and let me just do this briefly. If I look at sigma for the case that U is also in the image of F, so some F of X prime, then this is the same as we start from this situation. I use the fact that F is monoidal to write this as F of X tensor Y, and then I use F of the braiding to write this F y, no, f prime, obviously x, and then I use the inverse of this, of the isomorphisms, to go to f of x prime tensor. That this combination is the same as this sigma, and then the second property, which maybe I draw graphically, I use for this sigma a symbol like that, where these are now this would be f of x and this would be u, and then we looked at a situation that here we have a tensor product in V. And I can do this in 2 steps, using the sigma describing u here, and then the sigma with u prime. And then third, analogous thing for, maybe I don't draw this, you can do the same for if you consider sigma f of x, density f of x prime, and any u, then you can use the tensor structure here to have 2 lines labeled f of x and f of x prime. And then so you have the tensor product in terms of these punctorial boxes. I meant that sometimes this would look like that, and then you can use the tensor product here, and then you can multiply this again, and so this would be this situation, and again you assume that you can do this in 2 steps. I don't write the labels. And now, in the case of our functor that we have here, you see that this actually gives FA the structure of a central functor. And we indicate how you show this. Maybe not using colors, because this takes unnecessary time. So we look for the first step here at the situation that we use f on both x and x prime, and then take their tensor product in the boundary, or we first, via the braiding, move x to the other side, and then bring them to the boundary, and then tensor. Then the second thing, so this would define, this would define sigma, and this would be this particular property here. And so this is the situation where the x prime brought to the boundary is my m that I have here. And then the second one would be that again I have u and u prime. So I have 2 insertions on the boundary, 2 line insertions. And one bulk insertion which I can bring to the boundary, then use sigma to go here, and then go again the next step. But I can also say I first take the tensor product here, and then go in 1 step. That gives the second one, and the third one is the analogous thing where I use the tensor product in C. So I have 2 x and x prime here, which I either can first use and then bring to the boundary, and then use sigma, or I bring first both of them to the boundary, then I use sigma to move one of them around, and then I use sigma to move the other around. And you can check that this gives the same thing. Then there's an important result about such central functors due to David of Meganic's Ostrich that the structure of central functor on a functor f from C to R. Now I call this A. That's the reason why I was mistaken. This is equivalent to a lift f tilde of f to a lift of L, where this is braided functor from C. Remember, C was braided, D not necessarily braided, or A now, but to get something braided, I take the Drinfeld center. So we start with our functor F. We have the forgetful functor from the Drinfeld center to A, and then there must exist such a lift. And from this, it follows, since we have the structure of a central functor, that we have a braided functor and a tilde from C to the center of WA. And for various reasons, it is natural to postulate that this is actually an equivalence. I mentioned that a typical characterization of an equivalence is that it's essentially surjective and fully faithful. And actually, one of the two properties you can prove. Unfortunately, I forgot which one and I didn't look it up. But the other one we have to assume. Side remark here. In particular, if C is not the Drinfeld center of any fusion category A, then no topological boundaries exist. Now this can be formulated with the help of what is called a Witt group of modular tensor categories. There are actually various versions, maybe only braided fusion categories. And you have to be careful when you read the literature what is called a Witt group. But anyhow,
I think for topological application, you actually need ribbon. You need ribbon
in any case, but whether
also you can change the pivotal structure of C so that it's not ribbon and then
absolutely yes. But to be on the safe side, I'm using this here in our situation where we have a modular tensor category, and then we have a natural a spherical pivotal structure, which I a preferred or distinguished one, which I would then use. And maybe I don't give you the definition of V group. Essentially, it says that two such categories are width equivalent if taking the linear product of each of them with the center of some fusion category gives you categories which are braided equivalent. And then you show this is actually an equivalence relation, and you consider equivalence classes. Well, the linear product is the group multiplication, and the inverse comes from reversion of the braiding. So now this finishes what we can say about a single boundary condition. We still want to do two more things. And the second is to talk about defects. That will be, as I said, easy. The first thing still is to say what we can say about all boundary conditions. Of course, if you have a boundary condition which we call A, we now know there will be such a fusion category WA and a functor which is actually a sample functor for that. And then, of course, if we have now a second one, A prime, then there will be corresponding things. But that simply means we can have a lot of them, and we don't have any nice structure. So that's not the way we will look at this. But we will instead now look at allow for generalized one-dimensional defects, mainly not on a boundary, but boundary changing defects. So I'm now again in the boundary. And I can assume that defect such that on one side I have boundary condition A, and therefore category WA. On the other hand side I have WA prime. And again there can be insertions here. So again by the same arguments as before, this will be a category which I denote by WAA prime. And then I can consider the situation that I take the WA line here and fuse it with this line, and it should make sense. And analogously one from the side. So from this, you would expect that WAB is left WA module, and the right WA prime module. But now, also from the fact that this is the left WA module, it follows that this is I call it, let me see. Why didn't you complain? This should be A prime. If you remember these functor categories that I mentioned at the beginning today, in the context of bimodules, we have this notion of dual category. If I take the dual category for WAA prime, then if WA is left category here if
no, you don't write that.
Let me see.
You write WA prime and subscript WA prime. WA,
Wait, WAA prime is the category here. Yeah, WA and
Yeah.
WA prime. So
when you write dual category, you write C and M, right? CM star.
yeah, let me see.
Yeah.
W
A and then sub WA prime
W
and then star.
WA
Yeah.
WA prime.
Yeah.
Okay.
Yes.
And let me see. No, wait.
The WA prime is the dual.
Yeah.
Yeah.
So, and that should be the right module here. Only here. So it's both the right module for this category and over this category. So the simple thing is that naturally you would expect, or you would restrict to the situation that WA prime is WA prime sub. Which means in particular that I didn't mention that, but that we can show in the case that we are, that the Greenfeld center of the two are braided in. And now, no, sorry, it's correct, but this is not what is relevant here, but this follows from our arguments before. And this is now a good check because it is known that actually in this situation you have such a braided. So in a sense we construct that braided equivalence. A side remark. If we look at the regular C module category, then we can we can pull back the regular module action along one of these functors f that we have defined, and this way we get a structure of C module category on each of these WAs. But in the if X is in C and U is in WA, we define this as F of in WA and here. But important, this way we do not get all the modules. So the class of such categories is not a category of, but actually by category of C module categories. In any case, what we have achieved is we have a single boundary condition A. I think we have such a category A. We if you have from this here, we see that for any module category M over WA, via this interpretation, we get another boundary condition, A prime. And we know that set of WA is braided equivalent to C, and then also the same for A prime. But if two centers are braided equivalent, then this means that WA and WA prime have equivalent bicategories. Of module categories. And here I'm forced to use bicategories, which I haven't introduced yet, but we have talked about them last year, and you just should at this point accept that there is a notion like that, which is a three-layered structure, as like categories are two-layered. And that means that no matter with what A I start, if I look at this description, then I will get the same bicategory of boundary conditions. And that's about boundary conditions. Then, as I said, if we go to topological defects, it's not really harder. So we have our boundary condition. We have now a defect B between regions labeled by C and C prime. But I can forget about this part and regard this as a boundary condition for C, or I forget about this part and regard C as a boundary condition for C prime, taking care about orientations. So that means in this case, I get two sample functors F B from C to some category WB, and F to B from the other side from C prime. And actually, well, they are central functors. And again, I assume, well, with what I already have assumed, we have then braided functors, that these are equivalences. If both of them are equivalences, this in particular means that the center of C prime is braided equivalent to the center of C, meaning that such topological defects between regions labeled C and C prime exist if and only if C and C prime are in the same class in the bit group.
No, it's C to center of WB.
Thanks. And
then C is equivalent to C prime.
so
Yeah, C is equivalent to C prime.
Let me see. Wait. No, wait. Using that the center is braided, I can combine this to get a braided functor from C1 box times C box times C prime reverse to the center. That's what I want. And again, well, then you argue that it's equivalence, and that means that C and C prime have to be in the same class of the width group. Yeah.
Oh, we already have their equivalent as categories.
As categories, yes, but using that this is braided, you can argue that you have a braided function.
Then to center of W.
No.
Well, if it's equivalence, then the dimension doesn't.
No, you're right. Let me see. What did I? No, you can. You certainly have by just taking the linear product.
Yes, then it's not equivalence. We just have.
Yes. Well, in our case, C is
functor. Okay, we didn't have
C is modular. I don't have the details here. Maybe I should look this up and.
Yeah, I'm just concerned about this equivalence. We have a braided functor from C box C prime reverse to center of
Yes.
WB, but it's not equivalence. It's just a braided functor.
I can argue that there is an equivalence, and therefore this means that this is trivial in the width group, meaning that C and C prime are in the same class in the width group. And I didn't notice this when I wrote it down. So I have to look up the argument. I don't remember the details. Time is almost over. Let me see what else I want to say. Well, it's essentially two things, namely. Case it's equal C prime. Then what you get, assuming this is correct, then you know there is an equivalence because C is a model of using categorical. And then it's natural to say you have this, and then we may choose WA just to be C. So this particular defect for this, well, which is not so surprising because C itself, I can of course choose by simply saying that my defect surface is invisible. Then lines in the defect are just ordinary ribbons, and then I can take, according to what I said before, just the modules over C to get. So in this case, the defects are labeled by the modules, which at first sight sounds a bit surprising because somehow you might have expected bimodules, but that is not true. Rather, that you get in a different situation. Assume that C is not just a modular, but it's even bit trivial, for example, of some A, and analogously for C prime. And then you see that C box times C prime reverse is isomorphic to set of A equivalent, great equivalent set of A, the linear product with set of A prime reverse, which by interpreting the grading refutably is the same as the center of the product, and then you see that you indeed in the case now that also A prime is equal to A. For this case here, you deal with A box times A modules, or reverse. You have to be careful, and this is the same as A bimod. But it's A bimodules and not that. And now time is over. Final remark: you can actually get also on in the general case for general defect on this category here on the category WB by with the help of the forgetful functor C prime bimodule structure, but you do not get all bimodules. So and even already in rather simple cases, you do not get all of them. When I don't know a case where you do, and this is in particular relevant for one thing I did not mention. Of course, you would expect now that you can also fuse these two-dimensional defects. So there should be a tensor product on these, well, actually bicategories, but naively you might think that you do a kind of relative the linear product over the modular fusion category in between, but that's not the right thing. And actually, there is a paper from 2-3 years ago where there is a description is given, and they use 3 categorical tools for that. So, but I cannot say anything about it. Okay, thank you.
Oh, I have to take a picture.
When we get a few more people in.
It's raining and
It was the rain, yes.
yeah. Oh, I see what you're. We should have just this function. We have this to WB, both to WB, and if you fold it, we will have B as the boundary.
But that's one way, yes. Yeah.
The prime reverse. Yeah. Then we have this.
Okay.
Yeah,
okay.
Because
yeah.
So if you use F prime, then it's not. So this is F, tensor F.
Yes.
Yeah, so not F prime and not F tilde and F.
And then
yeah, because F tilde.
Then go to the tilde, then you have to do.
And then we can make
center.
Yeah.
Okay. Yes.
And here is should be a.
There should be a tensor off. Yeah, tensor. Well, that's what I. Well, okay. Let me see. I avoided to use this folding, but only because of lack of time.
Okay.
Actually, I wanted to make it. I would like to make a comment on that.
Okay.
So this actually shows that this folding works completely well. Is completely under control in this situation. Some people still call it the folding trick, but this is very confusing because in two-dimensional conformal field theory, people also talk about folding trick, where they do something analogous, but in that case, it's really something which is not working in full generality, according to me.
I see.